Kinetics homework number 1. Regardless of the questions that I'm asking you, make sure that you can answer the questions if it's a 0, first, or second order reaction. So we're going to start with the decomposition of a compound AB, and we're told it's 0 order in AB. Here's the rate constant. How long will it take for the concentration of AB to decrease to 29% of its initial concentration? Well, in order to do this, you need to remember the integrated rate law for a 0 order reaction. So writing that out briefly, now we can plug in what we know. Now we were told that, or we are asked to find the time, so we're going to know everything else. The concentration of the compound, which was AB in my example, so I'll be consistent. The concentration of my compound initially, you could say it's 100. You're going to pick an arbitrary value. The K was given to you, and that was 5.61 times 10 to the negative 3, and we're looking for T. The concentration at some time is going to be 27%. Well, if we pick 100 for our arbitrary value, then 27% of that is 27. So that makes that part of the calculation easy. And it shouldn't matter what you pick for your initial concentration. If you do the 27% correctly, you should still end up with the same value. So I subtract 100 from both sides, and then I divide both sides by my negative K, and you should get a time is equal to 12655. Now the unit for that is seconds. Coming back here, it says enter the value to the nearest minute. So I need to divide this by 60 in order to get my minutes. And then I get 211 minutes. That's my nearest minute. Number 2, again, be able to work this for a 0, first, or second order reaction. So we're given this decomposition. AB reacts to form A plus B. And one of the reasons I'm using generic items instead of compounds is I don't want you to get hung up on the compounds. So it doesn't matter what we're decomposing. If a plot of 1 over AB versus time is a straight line and we're given the slope, then you need to answer these questions. So you need to be familiar with what are your linear integrated rate law equations. And actually that's number 3. They're a little bit out of order. But you should know that a plot of 1 over AB versus time being a straight line means we have a second order reaction. And because this is second order, then the slope is going to be equal to K. So this is second order, which makes the slope of a 1 over AB versus time equal to K. So the K is 0.775 because we're told that that was the slope. So what is the rate law? Again, we're told it's second order. It's simply a decomposition. So the rate law is going to be the K value times the concentration of the reactant squared. Now to enter this in here, of course the 0.775 should be fairly intuitive, but you're given the rate equals. So now you need to enter the other parts. Now because we don't get a text editor with something like this, you're going to need to use the caret symbol, which on my computer is Shift 6, and then show me the second. So now we can calculate the half-life. Again, because it's second order, you need to know the half-life equation. T1/2 is going to be equal to 1 over K times the initial concentration. We were told use an initial concentration of this if it's needed. So we're given our K value, 0.775. Our initial concentration is 0.150. That was given to us. So calculating this, you should get a half-life of about 8.60 seconds. So what are the concentrations of A and B after 90 seconds? This part can get confusing, so make sure you work a couple of these. So what is the concentration after 90 seconds? Well, we have our integrated rate equation that looks something like this. And what we're looking for, however, are the concentrations of A and B. But in order to find the concentrations of A and B, I have to find the concentration of AB after 90 seconds. So this is what I'm not going to know, and I'm going to calculate with everything else. So the K was given to me as the slope of the linear line. We determined it was second order, which is why I know that that's the slope. And then I have 90 seconds here. So I'm going to add that to the reciprocal of the initial concentration. Reciprocal is just 1 over. So when I calculate this, I get a 1 over AB at time is going to be 76.416, and that repeats. So I take the reciprocal of that. What that means is I take 1 and divide it by this business here, and that gives me my AB. So my AB is 0.0130, and it keeps going. Now this is the concentration of AB after 90 seconds. So we have to go back to our initial decomposition reaction that looked like this. So remember, this is similar to an equilibrium expression. If we remove some amount, then we create some amount. But here, after we've reacted, we have this amount left. So what is X here? X is the concentration of both A and B. So that means 0.15 minus this will give me X. So that means that X is going to be 0.1369. We can only report 3 sig figs, so what we'll report here is 0.137 molar. And that's going to be the same concentration for both A and B. Number 3, we're going to type out the integrated rate laws. So this is a little bit out of order, but you know, it's good practice anyway. So the zero order reaction, A sub T equals a negative KT plus the concentration of A sub 0. So that is A at time, and then A initial. Now I'm going to use the text editor, and I'm going to make these subscript, and then I'm going to show you how this goes quickly. So if I copy and I paste, so I have first, but I'm still in subscript. So let's correct that briefly. Now, when I do this, all I have to do to make it 0 to first is add the natural log. So the ln of each of my concentrations. This time I'm going to learn from my mistake. And then so my second order is going to be the reciprocal. So I put 1 over. I have to remove that negative sign. And that's how you can remember all 3 of your integrated rate laws. So we're also asked for the units of the rate constant K. Well, for the 0 order, the units for the rate constant K are molarity per second, molarity over seconds. For first order, it's 1 over seconds. So you can either type 1 over S, or you could do S superscript -1, either way. Now to take this into the second order, all you have to do is add a capital M, or insert, that would be a better way to say that, insert a capital M for each of those, but it's underneath the fraction. So it's 1 over the product of molarity times seconds, or M to the -1 times S to the -1. Number 4, using experimental data, we're going to determine the rate law. So this is similar to your lab. So what I'm going to do is take this data here and calculate. And then it says to explain what the order is with respect to each reactant. So I will start with my data. And what I'm looking for, I know my rate is going to be equal to some constant K times the concentration of my reactants raised to a variable, which I don't know, or raised to an exponent, which I don't know. And that's what I'm going to be calculating. So first I'm going to compare number 1 and number 2. So if I go 1 versus 2, what I'm going to do is put the rate, 0.00300, over 0.450, give my equal sign, and then I have my K. Now I'm going to write out each of these reactions as it is, and then I will do my canceling. So 0.10 raised to the n. So the n value, NO value, 0.10 raised to the m, and then the Cl2 value, 0.15 raised to the n. Now I'm going to cancel out what's alike here because that'll make it easier. And then I do some algebra 2 on it. So when I have my 0.003 over 0.0045, this is actually a ratio of 2 to 3. So it's 2.10 raised to the n, and this is my Cl2 that I'm working on, over 0.15 raised to the n. Now comes the slightly more advanced algebra technique where we take the log of both sides. So if I take the log of 2/3, that's going to be equal to n times the log of these numbers, 0.10 over 0.15. Well, this also happens to be a ratio of 2 to 3, and that's why I left it that way, because the log of 2 over 3 divided by the log of 2 over 3 is just 1. So n is 1. So I can erase that and put my 1 in here. That's what I have calculated. So now I'm going to calculate the m value. Again, this is just like you did in your lab, or you will do in your lab, depending on where you are in the work. So now I'm going to go 1 versus 3. So when I go 1 versus 3, my Cl2 stays the same. So I'm going to put my rate over my rate. That's going to be equal to K times my NO value times my Cl value raised to the n. And I'm not going to put that 1 in yet. 1.5. And then my 1.0. And the reason for that is because they cancel out anyway. So my K's cancel. And now I'm left with my rate versus my rate is equal to 0.10 m, 0.15 m. So in this case, I actually worked out the numbers because they didn't work easily into my fractions that could simply cancel. So now I have my decimal form, and that's going to be equal to this over this. So I'm going to take the log of both sides, and when I do that, the exponent comes out, and then I'm taking the log of the numbers themselves. And I perform that arithmetic, and I get m is equal to 2. It's actually 1.998 or something goofy like that. We can round that. That's all right. So m is 2. So my rate law is then rate equals K times this, but I'm not done because a rate law will have numbers, not variables. The only letters that should be part of a rate law are the chemicals themselves. So I'm going to take just one of my experimental values here and plug it in so that I can then calculate my K. So to do that, I'm just going to use trial 1 here because it's here. 0.00300. It should be the same regardless of what you use. Plug in the value for NO, 0.1, square it. Plug in the value for Cl2, 0.1. Yeah, you leave that one alone because the exponent is 1. And then solve for K. So I get a K is 3. So when I report my rate law, I need to report it as rate is equal to, I should be typing this, rate is equal to 3 times the concentration of NO squared times the concentration of Cl2. Use your text editor to make sure that the superscripts get superscripted and the subscripts get subscripted. So that is my rate law. And then the question also asks me to explain what the order is with respect to each reactant. The rate is second order with respect to NO. The rate is first order with respect to Cl2. That's all I'm looking for with that problem, but you have to be able to say those words. Number 5, the rate constant for decomposition of this to this in the gas phase is given here at a temperature, and then we have another rate constant at another temperature. So if we assume the kinetics are consistent with the Arrhenius equation, we're asked to calculate the activation energy of decomposition. This particular problem is going to require you to do a couple of different calculations, and they aren't hard, but you have to understand the relationships. So we're given K and we're given T. So the K at 1.66 is at 650 K, and at 7.39 is 700 K. Now, assuming that we are consistent with Arrhenius, then what we can do is take the change in the natural log of K over the change in the temperature. That's going to be equal to the activation energy over R. So I need to find the natural log of K. I left out a negative here. The slope is the negative EA over R. So my final answer should be a positive. And I need to find, I put T, it's the reciprocal of T. And I need to find 1 over T. Now you could create this chart or you could do it in your calculator. I opted to do it in my calculator, but just briefly to show you the numbers, and I have a reciprocal button. It's an x to the -1. I find that very convenient and it keeps all my numbers together. But the natural log of 1.66 should end up being about 0.5068, where the natural log of 7.39 should end up being about 2.00. So the reciprocals here, the reciprocal of 650 is something like 1.538 times 10 to the -3. Again, if you can do this all in your calculator to avoid rounding error, that's going to be best. 8 times 10 to the -3. So you see these numbers can get a little hairy. But if you, what I do in my calculator is I actually type the natural log, and then I'm given an open parenthesis. I put my 1.66 and I close that parenthesis. And then I subtract the natural log of 7.39, close that parenthesis. And I actually get that answer before I divide it by, and then I put an open parenthesis. And I have 650, and I can raise that to the -1. That's the reciprocal. And then subtract the reciprocal of 700. And when I do that, I get a value of -13589.1221. It's enormous. But that number there, if you've entered everything into your calculator correctly, that number is equal to EA over R. Now, R we know. R is the ideal gas constant, but when we're working with energy, it's 8.314 joules per k mole. So what we're going to do then is multiply both sides by this 8.314. So I get an activation energy is equal to a -112,979 joules. Now that's a really big number. It says to enter the answer in kilojoules to the nearest tenth of a kilojoule. So kilojoules, I'm going to go over 3. That makes it kilojoules. I'm asked to go to the nearest tenth, and I have a 9. Look next door. It's going to go up. So I would actually report a -113.0. Now, you should also be able to define things like the rate of a reaction and the factors that affect it. So talk to me about concentrations and pressures and what does and does not affect the rate. Tell me about how when increasing the temperature, you increase the kinetics, the movement of the molecules, and that increases the collisions. And by increasing the collisions, you can increase the rate. That's what I want to see with that example. And use an example. Find a chemical reaction that you can describe specifically those factors.